Welcome students to lesson number 12, in which I am going to discuss on GPS data preprocessing. There are different ways how GPS data can be preprocessed. Among them, one of the method is the method of differencing, which I will be discussing today. Now the method of differencing will be discussed under the following heads like introduction. Then there are three types of differencing which we will be discussing: single difference observables, double difference, triple difference, then followed by summary of this class. Now as we have discussed in last classes that GPS observables are fraught with errors. That means there are some inherent errors that comes into the GPS observables, and that reduces the quality of the GPS observable, and as a result if we make use of those GPS observable for GPS positioning, the position information will be associated with some error. So in order to reduce the amount of error in GPS positioning, we need to reduce or eliminate the errors associated with the GPS observables, and that can be done by transforming the GPS data by taking the different types of differences. So now actually this differencing can be done in different ways, but we have seen that there are three ways how differencing can be taken and really end up with some effective observable which can be used for further processing. Now as we had discussed in the last class, GPS observable there are two types. One is that pseudo range between receiver R and satellite I. This pseudo range basically consists of the geometric range between the satellite I to receiver R and at any instant of time t. Suppose this is the observable we have in the GPS observation, and at any instant of time t or at any epoch t, this is the value we get, which this value will consist of this geometric range plus the receiver clock error, then it will consist the satellite clock error, then it will contain the ionospheric error, then tropospheric error. Now here you can see that all these tropospheric error, ionospheric error, these are dependent on the epoch of observation. That means at each epoch the errors may be different. Then satellite receiver hardware error, then satellite hardware error, then multipath error and random error. So this is the expression, this is the contents of the pseudo range observable. Already we had discussed in the last class. Similarly we can also go for the carrier phase observable. So I will like to take only the example of pseudo range. Similar expression can be written for pseudo carrier phase observable also. Now in single differencing, as I told you, differencing method will provide us the pseudo range free from the many of these errors, and there are three ways how differencing can be done. First one is called single differencing, then double differencing, then triple differencing. Let me start with single differencing. There are three ways how signal differencing can be done. Now, in the first case we may take the differencing means taking the difference of this observable, that is called differencing. Now, differencing, signal differencing can be done in three ways. First, we may take, suppose this is the terrain, where we may take observation at numbers of stations. Suppose this is the station A and this is the station B. Now, and the satellite is moving, suppose this is the satellite I. So, in case of the first one, let us take the first case where we will take the difference of observable between the receiver placed at A and receiver placed at B from the same satellite and at the same instant of time. That means two receiver from one satellite and from the same epoch. So what will happen if we take the observable at the same instant of time, then the observable that is coming out from the satellite will be having the same error, space segment error, as we have studied in the last class, that the observables are associated with the space segment error, atmospheric error, receiver error and other error. So, the space segment error will be identical for this signal and this signal, and if we take the difference of this observable, then space segment error, that means error due to satellite hardware, error due to satellite clock, ephemeris error, those error will be eliminated, and also depending upon the distance of this receiver, the amount of atmospheric error also will be reduced. Now, the second case, instead of taking observable from two receiver, if we take the one receiver but two satellite at the same instant of time. So, what will happen? So, in this case we are receiving the signal at the same instant of time. So, the error associated with the user segment, specifically the receiver. So, receiver error will be eliminated, that error due to satellite receiver clock and other hardware receiver error, that means this one, then this one will be eliminated, as well as if the distance of the satellites are more or less near about, then the signal will travel from the same atmosphere more or less. So, the amount of ionospheric error and tropospheric error in this signal as well as in this signal will be more or less same. So, they will get reduced. So, that is the idea behind this thing. And the third one, in this case, what will happen, instead of taking 2 receiver or 2 satellite, what we will take? We will take 1 receiver, 1 satellite, but 2 epoch. That means the signal that is coming at epoch T1 and it will travel to some distance at time T2, we will take the signal, same satellite I. So the pseudo range from the satellite I to receiver A at T1 is this signal, first signal, this is the first signal, and the second signal will be pseudo range from satellite I to receiver A at any time T2. So in this case, as the signal will be travelling from the same satellite, the second will be P R A I T2. So del P pseudo range T1 and T2. This is the difference. This minus this will be, this is the difference. So this type of signal will be free from integer ambiguity. Integer ambiguity. So here it is written, difference observables by taking difference of the observable from the same satellite observed at any station, as I written here, shown here, but at different epoch of observation T1 and T2, satellite as well as receiver clock error, because it is coming from the same satellite as well as to the same receiver, the satellite receiver clock error and satellites as well as receiver hardware error get cancelled. So this will get cancelled, then this will cancel, this will be getting cancelled, this will be getting, no, not this one, but this will get cancelled, this will get cancelled. So and in case of carrier phase observable, integer ambiguity will be removed. So this is what in short about the method of single difference. By taking this differencing, we will get a new type of observables, and these observables are known as single difference observables. So by single differencing we get 3 types of observables. We get single difference between 2 receiver, that means A and B, from the same satellite at the same instant of satellite. So this is the new observable we will be able to get, that is why it is called transformation. And in this case single receiver but from 2 satellites. So here I can say the difference T minus difference pseudo range I P T, and in this case pseudo range at time T minus pseudo range from the to the receiver A from satellite I to from J. So now in the third case, the so it is the difference, it is the difference pseudo range difference T1 pseudo range to from satellite I to receiver A at time T2. So these, by taking difference, you can see there are different ways how we have taken the difference. So in this case we have taken the difference at the same instant of time from the same satellite by two receiver. In this case we have taken the observables to the same receiver but at from two different satellites at the same instant of time, and in this case we have taken the difference of observable to the same receiver from the same satellite but at two instant of time, and by using this way we can reduce, we can remove some of the errors and we can reduce some other errors. However, because the multipath error depends on the geometry of the satellites as well as the configuration of receiver with respect to adjoining objects. So, in no cases we can avoid the multipath error. So, after this another method of differencing we can arrive at, that is called double differencing. Now I will explain about the second type of differencing observable, that is the double difference observable. Now double difference observable, double differencing observables, actually double differencing observables are the difference of the single difference observable. Now in this case we have taken two receiver, one satellite in a single epoch of time. In this case we have taken single receiver observation from two satellites at the same instant of time, and in this case we have taken one station, one satellite, two instant of time. Now in case of double differencing, actually we will be taking the difference of this or this or this. So now if we take the difference of this, so it will lead to two receiver, two satellite, one a single instant of time, or here also we will get two receiver, two satellite, one instant of time. So you can see here that if we take the difference of this for two satellites and if we take the difference of this for two receiver, ultimately we will end up with the same type like del difference A B I J T. So whether we take the difference of this type of single observable or this type of single observable, we will end up with the same double difference observable. And if we take this one like so, we will take this for two receiver, so we will end up with the double difference observable A B I T1 T2. So what I wanted to say is that for by single differencing, actually we will be end up with three types of observables, whereas with the double differencing we will end up with the two types of double difference observables. So now if we see in this figure, observables from differences between two single differences, we will end up with the double difference observable, and two broad categories of double differencing. So this is the way, because if we take the difference of this for two satellites or the difference of this for two receiver, you will end up with the same value or same removal of errors. So it is this same type of observable. This is one category, and another category is that we are taking this single difference observable which is taken for a single receiver, and we are taken, if we take for the another receiver for the same satellite for the two epoch of time, we will end up with this double difference observable, and this is the second category. The first type consists of taking the difference of single difference observable obtained from a satellite observed simultaneously from a pair of receiver at any epoch of observation. First category of double difference can be obtained from this first type of single difference, difference of this first type single difference, or difference of this second type of single difference. Now double difference are free from, as a result of this, the double difference will be free from satellite as well as receiver clock errors. So this is the, and other errors get reduced. So this is the first category of the double difference observable. In the second category, as I have already told, we will be taking the difference of the first single difference observable which has been obtained from a receiver from a same satellite but at two instants of time. So we will take first a receiver A, then another receiver B, and then difference of that. So we are taking here from the same satellite to the two different receiver but two epoch of time. So that is the second category, single difference observable at two different stations from the same satellite, at two different stations but at two instants of time. So at T1, during T1 the satellite I was here, during T2 the satellite I was here, and the observables from that we will be taking from this receiver and this receiver, and then we will take the difference. So as a result of this, because we are using the same satellites, the integer ambiguity will be removed. So the differencing will provide us, that means for the carrier phase observable, if we take into consideration the carrier phase observable, then the integer ambiguity will be nullified, and the residual effects for receiver clock error due to time tag bias on the computation of the range term need to be considered if the separation between the station is large. Now if the separation is large, then we have to be a bit cautious about doing this thing. The multipath error, which is a function of satellite and receiver geometry. Now you can see the satellite and receiver geometry will be different if I go from here to here, does not get cancelled in the double differencing observable. Noise get increased with the each double difference operation. So this is another thing which has to be marked, because the geometry will be changed, so the multipath error will not be cancelled. Systematic error due to unmodeled atmospheric error are generally increased as compared to single difference. Another thing is there. However, double difference is the most popular differencing technique for relative positioning during GPS surveying, and most of the GPS positioning we do based upon the double differencing method. So double differencing observables are very much important for our GPS surveying, and we make use of double differencing observable for our GPS positioning, and for precise positioning specifically we should consider the double differencing observable. And the another kind which is also available, that is called triple differencing observable. Now triple differencing observable, from the name itself you can understand triple difference, the difference of double differences. So in this triple differences observable, we have to take two receiver, two satellite, and two epoch of time. So only one variety will get, one variety observable we get. So in the triple difference is like this. We may arrive at triple differences through defined channel, because first we can take 1R 2S 2T 1T for single difference, then we can go for 2R 2S 1T, and then we can go for 2R 2S 2T, or we can go for 2R 1S 1T difference of this, then we can go for 2R 2S 1T. So when I may go from here to here, or I may go from here, so I will be reaching to the same, these are the same. So and then we know we have 1R 1S 2T, this is the single difference. So from there I can go for 2R 1S 2T, or we may go for 1R 2S 2T. So this is the way how we can get double difference. So you will see, and then from there we may go for either way we can arrive to this. So triple difference, only one type of observable we can get. Now these triple observables are actually as we have seen here, a lot of reduction in data will be there. So the geometric stability of the satellites which we define by DOP value will be much deteriorated. So generally we do not go for, we make use of 3D triple difference observable for identifying the cycle slips and as a pre-processing for the GPS observable, because through triple differences also we will be able to find out whether the GPS observables contains some errors or mistakes. So if we can identify those observables will be taken out, and later we will make use of double differencing of the observables for our further GPS processing. So that is all about. In this way we can reduce the amount of, if we can eliminate many of the errors, we can reduce many of the errors, and we can clear our we can improve the quality of our GPS observables. And that is all about today's class. Now let me summarize that GPS observables are fraught with errors, and the quality of GPS observations or the GPS point positioning will depend upon the quality of the GPS observables. That means we need to eliminate or reduce the errors as much as possible. One of the simplest way how this can be done is the method of differencing. That means by taking the differences of GPS observable, we may generate new types of observables, and there are three ways we can generate it: single difference observables, double difference observables, and triple difference observables. Of this, the double difference observables are most useful for GPS data positioning. However, triple difference observables helps us to identify the presence or absence of cycle slip error as well as the mistakes or gross error, and as soon as those are being identified through triple difference observables, we can take out those observables, and the existing observables we may make use of double difference observable for further processing to find out the GPS position. With this I like to conclude today's class, and the next class I will like to take on GPS point positioning, in which I will like to mathematically deduce how the position of GPS receiver is being determined making use of GPS observables. Thank you.